So I think what I'll do today is I will, in the latter half of the class, I'll do some more file reading related things. But for right now, I'm going to take a step back and go, I don't know how many of you are still working on assignment 6. Can I see it by show of hands, those of you who still need to do assignment 6? Right, okay. So quite a few of you. All right, so let's talk about that for a minute. Assignment 6, I'm going to assume that if you've chose the more comfortable stuff, you're comfortable with the material. So in which case, I'm going to go over some of the bits of the cache and the first Mario and the cache. Okay. Now, so in case you didn't have the chance to really pick up on while loops yet, while loops are essentially repeated ifs. Okay. While loop.py. A while loop is just a repeated if. As long as the condition next to it is true, right, it will continue to run. So for instance, if I have something like this, I is equal to 0, done is equal to false, while not done, I is equal to I plus 1 if I, oh, thank you. I knew that. I was just testing you, obviously. No. All right. So let's go ahead and see this. So a while loop, for those of you who need review, I is equal to 0, done is equal to false. While not done, I is equal to I plus 1. If I is if I is equal to, greater than or equal to 10, because I like to be very defensive like that, done is equal to true. What we'll do is we will print I before we call it, and so this will print out the numbers 0 through 9. So first and foremost, why did I write it like this? Most languages, Python is not one of them, you can write any while loop as a for loop and any for loop as a while loop. In Python, you can use a while loop to do any functionality of a for loop for the most part. Okay, or a lot of the functionality of for loop. Python tries to separate them a bit more, but for things like counting, you can use one versus the other. However, in general, they exist for two different purposes. For loops are what we call definite loops. Formally, they are definite loops. Because they are definitely loops? No, because they run a definitive number of times. Now, we may not know what that time is in advance for x in range n, and we don't know in advance what n will be, but we can say once n is declared, it will run n number of times, right? Whereas, or basically, we can say for x in some kind of string, right, that x will run for each letter in that string. Or for x in a list, it will run once for each item in the list, right? It will run a definitive number of times. You can calculate how many times it will run. For loops are good for that. While loops are good for indefinite. Loops. Indefinite loops. Meaning we don't know how long this is going to run for, okay? We just don't know. So these things are good for like being able to guard against user input. So the user puts in something and that thing is wrong and we need to keep telling them, and rather than crashing the program, we are just going to keep telling them to put something in until they do something correct. Make sense? So that is what we're going to use our while loops for a lot of the time, to basically say, while something is not done, keep doing it. Or maybe we use it to want to repeat our entire program. So while loops are good for when we want to basically say, I often write them in this format. While not done, and when a condition happens that I want to change it back to done, I change it to done. So in the case of lab 6, one of the things we have to do is that we have to define a Mario function. And this thing, I really like to break up my tasks, you see, into functions. And that's what functions are good for. For instance, Mario, we're going to be printing the staircase. So what I'm going to do is I'm just going to simply assume that the height I give my Mario function is going to work. Does that make sense? It's just going to work. Print stairs go here, right? It's going to work. This value is going to work. I don't have to check if it's good or not, right? This Mario function will do one thing and one thing only. Print the stairs. And I'll handle the user input outside of the function. Make sense? So user input would maybe go here. And that might be input enter height, please, right? Or something. It doesn't matter. Enter height, please. And what we'll do is we'll say height is equal to this value. And we'll go ahead and turn it into an int. Now, for the sake of argument, I'm going to assume, for the sake of convenience, I'm going to assume that the user gives me a number. So give me a second, size, height, comma, and then I will do this. Print size, height, stairs go here. Sometimes making a program that doesn't work is as useful as trying to start out by making the program that works. So first we define it, and then we run it, enter our height. I'm going to go ahead and enter 8. Size 8 stairs go here, right? We've got a successful placeholder there. If I run it again, though, and enter some big number, let's go ahead and try that again. Size 4234 stairs go here, right? Now, what we would really like to do, according to the specifications of the program I wrote, is that the stairs should be 1 to 8 inclusive. Right? Valid values 1 to 8. Right? And so I can ask them, and if they give me a value, great, but if they tell me something like this, if they give me a value like, give me a second. If I am given a value like this, 234, I need to be able to do something with that. I need to be able to say, no, that's not good. Does that make sense? We need a rate of rejecting this. Okay? So what we could do, now you might think, okay, if height, right, is not in this good range, we'll ask them again. But we don't necessarily know how many times the user's going to mess up, right? So if, let's see, 1 is less than or equal to the height, less than or equal to 8, those are our values. And what we could do is just simply ask them again. And the easiest way to ask them again is just copy paste this line. Make sense? So here I will enter 9. That's fine, and it says that's fine. 9 stairs go here. Ew. Oh wait, actually this is if it's a correct value, ask it for them again. I need to say that. If not in the good range, right? If not in the good range. Or you could alternatively say if height is less than 1 or height is greater than 8, right? It will ask them again. Oh, need a colon there. Now it's asking me again. I will say 90. It'll ask me again, and I'll say 5, and it will be happy. But as the input examples show, I want to be able to say 90, 89, 88, 87, and keep going. So fortunately, changing this from an if statement to a while loop is super duper easy, because all we have to do is change that if into a while loop. And that's it. That's how we, and now, watch all we have to do. So if I put in a bad number, another bad number, another bad number, or another bad number, doesn't matter how many times, as long as this clause is true, the height is less than 1 or the value is greater than 8, it's going to keep running. So as soon as I put in 8, I go into the main part of the program where I draw the stairs, and now I can just work on the for loop to draw the stairs. Make sense? So that's our while loop. This is where we can see how we can do a while loop. Okay, so that's for Mario. What about for coins? So what about the coin problem? The coin problem is about the simplest variation of the change making problem there is. The hardest variation is given this amount of money and these currencies, tell me how many ways there are to make change. We're not asking for that though. Here, and if you're interested in that problem, that involves something called dynamic programming, so it can be rather challenging. But for this problem, lab 6, cash, I already had it open. We are assuming that we have these 4 basic coins, even though the penny is apparently done. We have 25 cents, 10 cents, 5 cents, and 1 cent. And what we want to do is we want to minimize the number of coins we give out, okay? In other words, we want to say if we have to make 62 cents worth of change, we want to make it with the minimum number of coins total. So it'd be 25 to give out 50 cents, a dime to give out 10 cents, and 2 pennies to give out 2 more for a total of 2, 1, 2 for 5 coins. Make sense? So we're counting how many coins it takes to make the optimal amount of change. Did that make sense? I see confused faces. Okay. The algorithm I just applied to figure that out is something called what they call a greedy algorithm in here. Greedy algorithms are basically a class of algorithms, a class of strategies where making the best possible choice towards a solution right now actually gives me the best solution overall, right? Sometimes there's situations where making the most, right? This is not always the case, right? The algorithm of do what's fun now, have the most, the algorithm for have the most fun in life isn't always being greedy. Do the thing that is most fun right now. That doesn't work there. But in a lot of algorithms, it does. Here, taking the coin that makes the most change, that reduces the amount I have to give back the most, leads me towards the best solution. Right? Less than optimal solutions for some other instance of other problems. And that's fine because at least it's a solution for some problems. So, again, if we wanted, again, here's another example. Change owed, 0.41, and we get 4 coins back. Here, we ask for negative 0.41 change. We ask for foo. We ask for 0.41, and we then go into the problem. So this is basically 2 tasks here, if we see. this second task is calculating, given a valid number of change, how many coins do I owe, right? That's the second part of the problem. The first part of the problem is checking if it's a valid number, right? We ask that your user will be inputting a float. However, some customers will not do that. You'll need to create a function to detect whether a given string is a float or not. This can be used to validate your input. And I give strategies over here about how we figure out whether our input is a valid number. Okay? So here's what we're going to do. We need to basically create two functions to do two tasks. The first is create a function called isFloat, which is given some text. And that is going to return true by default. Okay? Sometimes it's just useful to define the functions even if they give me the wrong thing, because it helps us write what it's going to do. For this one, I'll go ahead and use a comment over here, some documentation, to say what it's going to do. It's true if text is a float, returns false otherwise. E.g. i.e. a good input for our problem that won't crash. Returns false otherwise. Okay? Def, and then the other part of our problem that we need to do, which is num coins given, and we're given a number, let's call it, given some amount of money, tell me how many coins that would take. And again, I'm just going to put a placeholder value here and say return 0 coins. Actually, no. Return, if we assume that money is, okay, let's write down some assumptions. Money is dollar is number in dollar dot cents. I'm using these, the curly braces as them called, kind of just to note that this is that these are not the literal world dollar dot cents. I could easily use this dollar dot cents format. Return number of coins, or minimum number of coins used to make this. You don't need to copy down these comments. I'm using them to kind of illustrate and remind you as we're working on this. I'm going to start out by just giving us what is an answer, although a valid answer, but the wrong answer. Okay? A valid but wrong answer, which is I'm going to return money times 100. What is that? Well, it's in dollar cents format, so if I multiply this by 100, right, assuming that we're working with proper cents, right, then there's only ever going to be 2 decimal places, so this turns it effectively into an integer, right? This is effectively the number of pennies I would have to give back, right? Because I'm multiplying by 100. There's 100 pennies in every dollar. So this is a valid answer, giving them just a sack full of pennies. It is the spiteful answer to give to someone you don't like, but it is an answer, even though it's the wrong answer for the problem. But it's an answer, okay? But we can attack that answer late in a minute. Okay? So what we're going to do now is we are going to ask ourselves, so now that we have this, we can test these things without ever actually taking the user input yet, and just test these things, right? And we can also, if we have an idea of how to solve one, we can work on that one independently of the other. That's the power of functions. It allows us to split our problem up into smaller and smaller things, So first off, let's tackle is float. We need to figure out true if this is a float. So, okay. Because what we don't want to happen is we don't want to basically take our input, right? We don't want our number to be something like this. And then try to convert this number into a float. Because we'll get an error. Oh, no, we'll get an error first because I have an accidental slash there. But we'll get an error saying we can't convert it. Make sense? So, what are we going to do? Well, we need to basically come up with figure out what the rules are for text to be considered a float. So let's go with as much basically rules as we can. First off, what are the valid characters a float could have? A floating point number could have. Forget about order. Forget about how many of each. Forget about all that stuff. What are the valid characters that a float can have? A floating point number. Right? There's actually a limited number if we think about it once you understand my problem, because this is not a trick question. Okay? Valid cars are what? Well, first off, if it's a floating point number, all the numbers are legal, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So those 10 characters are legal. What else is legal in this kind of string? What? The period, yes. The period is legal. Technically, the negative is legal as well, but we didn't want any problem. We didn't want any of our things with a negative, right? And so I'm also okay with leaving out the positive as well. Make sense? So just for our input, if we're assuming somebody's putting in something $cents format, even though it's called is float, I'm okay with like limiting it even further and just saying, hey, these are valid characters. Okay, this is great because now we have a very easy way of dealing with any idiot who puts in, oh, give me your change back. And he says, apple. I'm going to put an apple here because I want to see what's going to happen to the program. People like me do exist, and we do mess with this stuff. We are the worst. So the way we can do that is say for each letter in the text. And remember here, I'm using letter abstractly, right? 1 is a letter. Period is a letter. Slash is a letter. A, B, C, D, E, F, G are each letters, okay? I use letter instead of glyph because while technically we might call these glyphs, letter just makes sense, right? And for every letter in the text. For every letter in the text, if the letter is not in valid characters, valid cars, right? If our letter is not in the valid characters, we can immediately say something has gone horribly wrong, right? They did not give us something good. So what we'll do here now is we will return false. So an interesting thing about returning is that returning immediately says, I am done with the function. The function is done. I've hit my answer. We don't need to continue on. We can just stop here. Answer, done. Okay? So a common mistake I will see is people who will say, they'll see automatically, oh, if it is not valid, if they see an if, they'll immediately go, okay, it has to have an else, so I'll put a return true. And if you do this is a very common mistake, but the effect is you'll only ever check the first letter, because what you'll do is you'll take a look at the first letter, and if it's false, if it's not valid, you'll return false. But if it is valid, you'll hit this else and go ahead and return true, and you won't check any of the other letters, because once you hit a return, you're done. Make sense? So we only really want to quit if it's this. Now notice I have a return true right here at the end. This is a part I skipped and should have mentioned first. When we are doing these kind of functions that are is questions, is this a valid input? Is this a float? Is this, is this too big? Is this too small? Is this made up of unique items? It only has one of two answers, true or false. And so the easiest way to solve these problems is to assume one and then go through the steps that would disprove it. Okay? So here I'm going to assume the input is valid. That's why I have the return true here at the end. And then what I'm going to do is I'm going to go through the cases where I can figure out, okay, this is wrong. Make sense? So, and that might require some testing. Because think about if I try to do the other way around here. If I assume everything is wrong, I then have to try to prove that it is correct. And that feels a bit harder if I think about it, right? It's just easier to say, hey, it's wrong. Also, humans are great nitpickers. We love to say why things are wrong. Even if we don't like to communicate it to the other person, that varies from culture to culture. Okay, some cultures are very, very blunt and will say things are not great, and some other cultures, they'll edge around it, right? So if you're ever working with an international group, right, you got to know the culture there, especially if it's an international business, like with Japanese. Japanese like to be circumspect about stuff. They like to be a bit, indirect, depending on the culture. It applies somewhat, but in a very different flavor in Korea, right? These kind of things. So just be aware if you're ever working internationally to kind of understand cultural nuances there, even if you aren't required to speak the lingo. Okay. So, four-letter and other cultures go the complete other direction, where they are blunt to the point that it seems impolite. So, four-letter in text. If letter not in valid characters, return false. What other thing could we check to see? This gets basically things like, well, let's go ahead. We can try our input now. So we can say something like this, and use what we did last time as kind of a base. Let's call it value is equal to input and enter change. We'll put a colon and a space there. And we'll just simply do this. It's a bit different. We're not going to do a while done or whatnot. We're going to actually put the function right here as the condition. While not is float value. And then we do the same thing here. Does that make sense? So we get the value, and then we check, hey, is this value good? If it's not good, then this evaluates to true, right? So if it returns false, this not will make that return to true, which means that the loop keeps going, right? While it is not a float, it grammatically makes sense. While it is not a float, keep asking the person for it. And then what we'll do is that we will then do then once we know it's safe to transform, we will say value is equal to float value. So we are checking it first before we are transforming it. So over here, right, if I now enter apple, taco cat, negative number, big number, that's fine. So let's go ahead and try something else. 45.2, fine. 42.42. Unfortunately, that passed our tests, that passed our guardrails, and was considered to be valid, but transforming it made it invalid, right? The value we tested was, in case you missed that was we tested 42.42.42. And what made it wrong? What made it impossible to change into a float? Not a trick question, right? Floating point values have 1 decimal place. This would have been fine, but this, we have 2 decimal points here, right? Numbers only ever have 2 decimal points in American writing, right? Some writing will do decimal points like to do instead of commas, but that's not what we're looking for here. We're looking for a number that's basically some AAAAA.BB kind of format, right? We're not looking for multiple dots. So that's another way to know if this is a bad value. We check all the letters, fine. So we'll just make one more ask. If text.count, right? Nice and easy function, don't have to do this manually. If text.count, the number of periods, is greater than 1, if it has more than 1 dot, return false. Make sense to everybody? And we put this outside of the for loop because if it was in the for loop, we'd just check this we'd check this every time we have a letter. We only need to do this check once. If it was inside here, we'd basically if it was inside, we'd ask, hey, is this letter valid? Is there more than 1 period? Is this letter valid? Is there more than 1 period? The is there more period isn't going to change, right? That's why we keep it outside of the loop. So now, 42.42.42, we get asked it, and it's fine. I think I've accounted for basically all the cases here that we need to, because we don't have to worry about negatives or positives. We don't have to worry about the position of this period, right? Putting it as the front without any preceding numbers is fine, right? For instance, what I'm trying to say is that, right, doing something like this, AA.BB is fine, as well as .BB, .BB is fine, and AA dot is also fine, technically, although it's weird, and anyone who does that should be shunned. No, it's just, but I'm saying that basically none of these formats which are valid will break our program now. Okay? One other last trick we can do, if you don't like the fact that we are taking the input multiple times like this and we have this while loop that's duplicated, we could, and this is what I see a bunch of people do sometimes, I could put in a starting error value like this. It goes and checks the loop. It says, oh, that's not valid. Let me ask you to input something. To the user, it appears like nothing, right? But I've seen people do this. This is fine. This is perfectly fine. And so we just keep doing our stuff again and again. Everybody following along? Cool. So, you probably didn't expect me to be helping you with your homework so much today. So, well, thanks for showing up. So I know it was tempting to some of you to completely just skedaddle off to take an early spring break. It's tempting to me. I actually had a dream that I was sick and wouldn't be able to teach class today, and I was so happy because I wouldn't have to come in and teach, and I'd get an extra long spring break. And I'm like, well, that's a bit weird. No, actually, I enjoy this job. It's funny. It's just such a weird dream. I think I'm just ready for a break. Although it is weird that it is so early. It is very weird. All right. So how do we do this problem? This one is actually, again, as I wanted to mention, this problem is probably the most basic of a bunch of problems we can get. I'd say that the most advanced version of the problem, or the basis of the most advanced problem, is the following, which is Project Euler coin sums. I know, Project Gutenberg, Project Euler. Euler's a famous mathematician. This is a famous problem. I'm just trying to get directly to Project Euler. I don't need the problem. I don't need the answer. Oh, come on. There we go. In the United Kingdom, the currency is made up of the pound and the pence. There are 8 general coins in circulation. The 1 pence, the 2 pence, the 5 pence, the 10 pence, the 20 pence, 50 pence, the 100 pence or 1 pound piece, and the 2 pound piece. It is possible to make 2 pounds change for 2 pounds the following way. So that's one way to do that. One 100 piece, 150 piece, 2 40s, a 5, a 2, and 3 1s. How many different ways can 2 pounds be made using any number of coins? This is actually a fairly advanced problem. One that we've learned how to solve not in the next computer science class, not in the computer science class after that, but in 3223. Okay, this is uses a method called dynamic programming, or I think you can solve it recursively, but dynamic programming is the proper way to solve it. Very interesting problem, lots of variations of this problem. So if you're interested in it and have way too much time to spare over break, you can take a look at it. It is quite an interesting problem. And it is the same technique that you use to solve another problem called lattice sums, which you can look up here, lattice paths, which is basically, here's the number of ways through a 2 by 2 grid. There's 6. How many ways are there through a 20 by 20 grid? So it asks you to calculate those things. And these kind of problems are good kind of problems to really start on, but I would start on the simpler problems for you since you just started out. Again, some of these require higher and higher techniques. So, first and foremost, our values are we're going to be using the 4 values of quarter, dime, nickel, and penny. Okay. Now I could do subtraction with, by subtracting 0.25 and stuff like that. But honestly, since we're working with cents, it makes sense to convert this to cents. Does that make sense? The pun is not intended there. Does that make sense to everybody? Okay. I'm going to convert this into cents. And the way I'm going to convert this into cents is we kind of already figured out how to do that by converting it with money. We're going to take this money, multiply it by 100, and then to really drive the point home, I'm going to convert this into an integer, right? Since you can only have a whole number of cents, right? Does it make sense to everyone? Again, the pun is not intended. All right. So this variation of the problem is asking for the most simple thing, which is how many coins is that? So I'll say coins is equal to 0 and return the number of coins. Now, okay. So how in the world do we solve this? Well, there's a couple ways. The first is you can use division and modular arithmetic again, right? You can say, okay, if I have 76, let's go 77. If I have to make change for 77 cents, I can take 77 integer division by 3, right? Cents divided by 3. Sorry, not 3. By 25, and that will give me 3, which is the number of quarters, right? Or this will give me the number of quarters that I can make. I can say coins is equal to coins plus this value, and then I just would take the remaining amount of cents that are left over, which would be mod 25. That's the first way to approach it. Okay, I'm not going to explain that one any further because that's typically not the way you mentally do the math. Even though this is the most programmatically efficient way to do that, just simply do that for every single coin denomination. What's the other way to do it? How do you as a human being do this? Well, the answer is you start with the biggest number you have and you subtract from it as many times as you can, while the number of cents I have is greater than greater than or equal to 25. Does that make sense? 25 greater than or equal to 25. Cents is equal to cents minus 25. Coins is equal to coins plus 1. Now this strategy is the way you do it as a human, which is, okay, I can take a quarter out of this remaining amount of change. So I'm going to do so. So while I have more than 25 cents, I can take out a quarter. I'll take out a quarter by removing 25 from the total. And then I add 1 to the number of coins because I've just added 1 coin. Make sense? So 77 minus 25 brings me down to 52. Then I'll just continue. 52 minus 25 is 27. 27 minus 25 is 2. Oh, the loop stopped. Then just apply this for every other denomination, and you're done. All right. So that is the coin problem. It is not actually that hard when you get down to it. The main things you want to take away from my rambling, though, from my crazy rambling about this problem, is that the problem is often multiple. Your problems are multiple. Words hard. Okay. Your problems are often multiple problems that can be solved independently. So identify where your problems can be solved independently and split them up. It's a lot less stressful, a lot less to worry about. It makes things more organized. It works. Okay. Let's see here. Why do I have 2 of these open? Oh, because it's a GitHub. Okay. Okay. Now, let's talk a bit more about file reading. Okay? Or about files in general. Okay. So, I'm going to create a file called examples2.py. I'm not going to name it files because that seems dangerous. Okay. So, last time we learned about the open. Open can be used to open any file, any text file, like for instance the coinproblem.py that I just wrote. Okay. And call it data. I can open it. Okay. And then I can read it in one of 3 ways. I can do print data.read to read the entire thing and print it out as one thing. I can do data.read lines to read the entire thing all at once into multiple separate lines, right? And then I can do one more thing, which is I can do a for loop. To print out each thing one at a time. Each line one at a time. So the default for this is actually short for the default argument, which is coinproblem.py and then a second argument of R. R here stands for read. Now, if you wrote something called coinproblem.py, this next part is very important if you don't want to lose all the work you just did. like all the past 40 minutes of writing down my stuff. Okay? Remove this argument over here, the coinproblem.py, and just give it some other name of some file you haven't done before. Like, I don't know, foo.txt maybe. Okay? Everybody rename that away from like coin problem or something? Good. This will error and it has no ill effect even if you didn't change anything, right? Because a file is not found. We're trying to open and read a file that's not found. However, open can be used to do things other than read files, right? For instance, this is an R for read. And the existence of a read mode implies what? It implies there's a write mode. And this is why it's important you change this away from anything you named, because write creates a new file with this file name. Open that and it'll work. Now, mind you, if I go and check this out, let's see. If I go over here to my folder, documents, S1051, you'll see I have a foo.txt here with 0 bytes currently. Created a new file just for me. But if you name it something you already had that already had a name, let's go ahead and I'll just put stuff in foo.txt. I'm just typing random characters, doesn't matter. So now if I close this now and I run this, it erased my changes. Writing writes a completely new file. Okay? It starts a completely new file with this name. Okay. And so what we can do is that we can use this to not just output, we can do this as an alternative to outputting text, to printing text. We can instead say something like data.write. Let's go with hello, new line, data.write. It's not like a print where we'll automatically put in new lines. World, exclamation point. And then to make sure that let's see, this, if I recall correctly, boop, let's go ahead and open this. Will work, but the polite thing to do after you're done with reading or writing a file is to do the following. Close the file to say other things can use it. Reload. And that created this file called hello world. If I change this to hello, and now I change it to all caps world, and I run this file, and I run this program again, right? This is the previous version, reload, and you'll see that it overwrote, that my running this program overwrote what I previously had. Make sense? So there's a read mode, which is what we're going to use pretty much almost all the time in this class. Write method is worthwhile to know about, as is the other write method. There's actually two. Read, write, and then there's one more, which is A, which is not Q, it's A. A in this case stands for append. Because sometimes you don't want to delete everything in the file that already exists, right? Sometimes you want to add on to the file that already exists. So append is a non-destructive write. It opens up the file, goes to the end of it, and adds stuff to it already there. Run it. And now if we go to foo, reload, it went to the end of the file, put in hello, put in a new line, and put in world. Make sense? if I were to run it again, and again, and a third time, I'll just keep appending to the end. Make sense? All right, any questions before I go on to a more concrete example of stuff? Okay. So, part of the reason I have complete, you have to complete Lab 7 as one of the things that needs to be completed by a certain amount of time, which is week 11. By the way, week 8 would be the week we get back from break. Week 8 isn't the break, it is the week we get back from break. So, week 11, the reason we need this done, this file reading question done with the hurricane tracker, is because a lot of the problems I'll ask you in the future involve reading a CSV file. One of the questions on the exam will be, given a CSV file, please read it. Okay. Let's see, do I have any fun data for CSV stuff? I believe I do. Let's go to Documents, GitHub. Let's see. Now we will go to New Clone Repository. Choose Documents, GitHub. Select folder. Classroom. And this should be able to get what I need. Classroom. And then intro. Here we go. Pokemon.csv. I have been known to play a bit of Pokemon on occasion. The urge strikes me every few years or so. I've been playing on and off since the original Red edition. So I do enjoy Pokemon. My favorite Pokemon is probably Gallade. I enjoy doing dual battles with Gallade and Gyarados. Gyarados has basically helped me basically wreck teams ever since the very first game, so I'm very attached from it. And if you don't know Pokemon, it is worth at least kind of figuring it out a little bit, because it is the most profitable media franchise of all time. Period. It's made more than Disney. Well, media franchises. Pokemon. Total revenue, $115 billion. Mickey doesn't even come close. Look at that difference. Huge difference, okay? So, anyway, Pokemon's serious business. Now, at the core, Pokemon is a turn-based strategy game where you're trying to knock out the opponent's team using basically an advanced game of rock, paper, scissors. Only there's 18 different types of rocks, papers, or scissors. And some rock, paper, scissors are rock papers or scissor rocks. They have two types, in other words. Now, generally speaking, though, you can abstract Pokemon out like this. They have an ID, which is some kind of number. They have a name. Form you don't really have to worry about. Just know that there are just kind of different variations that can happen. Types, we won't really work about that, but that's the rock, paper, scissors game. And then they have stats, because it is an RPG. Attack, HP, which is basically hit points, or essentially the amount of life something has. Then you have attack, defense, and special attack, special defense. Attack and defense are more like analogous to physical blows, and special attacks are like being able to shoot energy beams or blasts of fire at each other. Defense is how well, attack is how hard you hit, defense is how well you resist it, and speed is who goes first. That's it in a nutshell. Also, total is just simply the sum of all these things. Simply put, the higher the total, the more powerful this Pokemon's probably going to be. It's not always the case. For instance, one of my favorites, a Pokemon called Slacking, is this big chunky boy over here, which has some ridiculously high stats, but he only moves every other turn. He loses a turn. He loses half the turns and can be played around like that. So stats aren't everything. There's traits and stuff, but we don't need to go into that. What's important here is that this is a large file, and while I double-clicked it and it opened in Excel, it is not actually a .xls format, which is the default Excel format thing. It is, in fact, open, a CSV file, documents, GitHub, Classroom. And if you are interested in playing around with this file, you can find it on my GitHub, which is linked to from Canvas, but don't worry about that for right now. Just follow along. Intro, open Pokemon.csv, and you see that this is a big CSV file. All right. Now, let's see. It looks like I already have some previous stuff written from previous semesters. So I'm just going to take a look at these and see what we have here. Yep, we did do a lot over here. Yeah. All right. And then run. Okay. All right. We're just trying to check what I did, if that was anything interesting there. So, okay. Oh, that was a good way to do that. Okay. Just curious as to what I did to figure out like some of the best. All right. So, we can play around by opening this file. And if you want to find it yourself, let me just be a bit more clear about, just go to my GitHub. Go to home. If you want to play around with this, and you do not have to, you're not turning anything in. But if I go to other important links, I have my links to my GitHub over here. It'll bring you to github.com/abrosen/classroom. And if you go to intro, the intro to Python folder, there will be stuff in there. And there will be a bunch of files. And if you click on the, it's sorted by type. If you click on the one on top, it's not sorted by type, just over here. Pokemon.csv file, right over here, is this file, and it's presented in a nice format, and you can hit download or raw to get access to it. So if you're interested in that. But I would just suggest, because I'm about to go quick, to just watch along. So this file is called Pokemon, with a capital Pokemon.csv. And I'll just simply call this again data. I'll save this in pokereader.py. Test that I can read this file. Yes, I can. Pokemon, by the way, is short for Pocket Monsters. So just in case you're curious as to where that came from. So let's go ahead and just test that we can read this. Data, let's go ahead and say lines is equal to data dot read lines. Print and then I'll want to illustrate one more thing I skipped. We read the lines. It has read the lines into the file. That's a lot of data. Continuing on. Next, the only thing I want to show you is that I forgot to show you back there was what if I like read the lines again? I don't get an error, but you'll notice that I have nothing in there. When you read a file, you go from top to down and then it remembers where you are until you close the file or start the program again. So reading a file, so you can't really read a file a second time unless you reopen it. So interesting quirk there, just why I mentioned it. Read the lines. Now, we've got our data. Now, commonly in a lot of tables, a lot of CSV files, our first line of data is not actually data. Everybody see this? Our first line of data is not actually data. It's a legend telling us what the data is. And if we try to analyze that, that's going to give us a bad time. Right? So, first off, let's just go ahead and just kind of see this by, let's close this. We can see this by, boop, boop. First off, slicing off, like the rest of this, and we'll just read the first 10 lines so that the data is much easier to read. You can see here that this is our legend, and we don't really need that. So we can get rid of the legend by saying, hey, I want my lines to be equal to just simply 1 to the n. So everything but the very first line. And if we do that, we see we start with 1, Bulbasaur, 2, Ivysaur, 3, Venusaur, 4, Charmander, 5, Charmeleon. So this is all correct. And so now we have all the data for all the Pokemon loaded up into lines. So what can we do with this? Okay. Well, what we can do is, and let's see, we could figure out some interesting stats. We could look at these things. For instance, we could try to figure out, for the beginning, which Pokemon has the highest ID. Sorry, not the highest ID. Highest HP. Okay? What is that? A lot of rumbling. All right. Okay. So what we'll do is we'll basically say highest HP is equal to 0. Name is equal to. And what we'll do is we'll say for line in lines. For every line, we need to now process that line. Now, it's a comma separated value. So this file, we can basically get to everything by just simply splitting the file on the comma. What do I mean by that? Like we did last week, here's the difference. Print the line, print line dot split on the comma. And I'll only do the first 10 lines so our view doesn't explode. There we go. Give me 1 second. Line, we've also have those new lines in there. So line is equal to line dot strip to clean out those new lines. And then We'll print the line. We'll print what it looks like after we split it. And then I'll print out a blank line in between these entries. And we see, here it is. Here's our string. This is line. And this is our string after we process it. And we can see that it split these commas up. So now that each field is its own individual item. Now, since all we care about is the HP and the name, those are the two things we need to focus on. So we had ID and we had name. So line.split, so I'm going to call this parts is equal to line.split on the commas, and parts 1, if we print that out, that's going to give us the names, right? There's the names of the Pokemon. It also prints out the quotation marks because those were part of the names. That was part of the data. But we can clean that up. Parts 1 is equal to name. Name is equal to name dot, and this is fun how to do this. Name dot strip. And rather than stripping that, what we're going to do is we are going to do single quotes there, have a double quote there to say target the double quotes. Print the name. And now the double quotes are gone. Strip removes preceding and trail. Basically, it removes symbols at the beginning and the ends of a string. Very, very useful. Okay. So we have our name. Now we also need to get the HP. HP was 0. Got to do some manual counting. 1, 2, 3, 4, 5, 6. HP is equal to parts 6, and then we got to transform that into an integer. No errors there. Print the HP value just to confirm that that is what we're getting. 45, 60, 80 for the first two, for the first three. That compares just fine. Okay. So now we are appropriately getting the name and we are getting the HP. Now, we basically want to keep track of who has the highest HP, which we've done something like this. I'm not sure if we've done something like this before. We found the biggest. But the way we keep track of well, let's just go ahead and show us. We keep track of what the highest thing we found is. And then at every step of the loop, we ask ourselves a very basic if statement. If the HP I am looking at right now is greater than the highest HP I have seen, then that highest HP I have seen is no longer the highest HP I've seen anymore. I've got to fix it. Right? If the HP I currently have is higher than the highest I've seen, HP gets stored in highest HP. And we'll go ahead and update the name. We had two names here, so let's go ahead and say highest name over here. And we'll say highest name is equal to the name. And then when we're done, we will print out name, sorry, not name, but print out highest name, comma, highest HP. This is why I used Geany, because that autocomplete is very convenient, but not like broken, groundbreaking, or AI stuff. And Venusaur 80, if you know Pokemon, you know that Venusaur doesn't have the highest HP, but he does have the highest HP of our first 10 Pokemon. Because we're only looking at the first 10 right now, just so that was easy to print out. So now what we'll do is we'll remove this slice over here. We'll just simply say for line in every line, run, and we'll find that Blissey has the value of 255. This is unsurprising for anybody who's played Pokemon. Everybody knows that Blissey, this Pokemon, has the most HP. This Pokemon has an absurdly high HP stat, which is 255, but it has like, let's see, yeah, 255, but it has no attack or defense. And so basically if you hit it with physical attacks, it goes down, but if you hit it with special attacks, it will just tank that. It's fairy. It's fairy Pokemon. Why 255? Because that, in the original Pokemon, was the max value for a bite. 2 to the 8th power. Max value for a bite. This is 2 to the 8th minus 1. 8-bit number. Which is what you could store in an original Game Boy. So, that's Pokemon with the highest HP. We could also figure out some other stuff, and because it's 313, I will just open up what I previously have done and kind of just gesture wildly at it, I guess. Okay. So, let's see. Here, let's go ahead and look at some stuff. I've taken the same file. I used explicit read right over there, but I called my lines rows instead. I said the file dot read the lines. And then I defined a num to track over here. When I make something in all caps, it's basically a way of saying it's not so much, it is technically a variable, but I'm not going to be changing it anywhere. It's a constant. Buffest. And what we do over here is we say for I in range num to track, which is 5, buffest dot append a small list. The list, so our list is getting lists of blank names and 0 buffness, I guess. So this will track which Pokemon are the buffest, which is the combination of attack, defense, and HP. So we're looking for which Pokemon have the highest combination of attack, defense, and HP. Okay. So what we did is that we said for line in rows, so everything but the first line, which is legend. We split it up. Oh, the name is the first part. The attack, HP, attack and defense were the next parts. And what we did is we calculate that the buffness is this combination of attack, defense, and HP. Okay. And then I did some nice, clever programming here. Here I took Type 1 and Type 2 because I was trying to figure out which was the buffest fire Pokemon, which were, or the buffest ones, which were Groudon, Ho-Oh, Reshiram, and surprisingly Blaziken was up there, but maybe not too surprisingly. Also, this isn't the most up-to-date Pokemon. I'm not sure what generation it goes up to. I think Sword and Shield. So, still got plenty of stuff, but let's go ahead. We'll go ahead and, I think, remove these lines right now, since we're just looking in general. So without that, inconsistent use of, oh, come on. Don't do this to me. Show white space. Oh, I'm sorry. Ugh, this is the worst part about Python, which is that it will try to do, is that it doesn't like mixing tabs and spaces at all. So, edit, preferences, editor, indentation, for use, detect from apply. Okay. So over here, tab, no. Tab, okay. Okay. Tab, boo, hiss. Okay. Edit, document, indent type, spaces. There we go. It was mad that it was identifying tabs here and I wanted spaces. So we run this, we find the most buffed Pokemon are Eternatus, Aggron, Groudon, Zygarde, and Steelix. And the way this works is that we calculate a Pokemon's buffness, so the combination of attack, defense, and HP. And then what we do is that I look at each of these 5 values I'm keeping track of which are the strongest. And I say, hey, let's look at index 0 first. If my buffness is greater than the buffness I have stored, because a buffness will store the name and index 1 there is the buffness of the saved Pokemon, I'm going to remove that and put the new Pokemon in where that old Pokemon was. In fact, I can, instead of, I suppose I use pop over there, but honestly, it is easier if I just simply say current. Let's go with buffest. Does this work? I think it does. Current 0 is equal to name, and current 1 is equal to buff, and no, oh, yeah, and then break to stop so you don't replace everything else. Metal Calyrex. So we did get a bit of a difference. Current is equal to index. I'm not going to question it at the moment. So there we go. We replace if. So basically what we are doing here is that we look at all of the Pokemon. We go index by index of the 5 that we are tracking, and we say, hey, if we find one that we are better than, then what we're going to do is we're going to take its spot. We're going to replace its data with our data to say that we are the stronger one, and we get that value. All right. With that, it is 3:20, and I've droned on long enough. Have a good spring break. I will be uploading this one and the previous lecture soon.